Video, I'm going to show you another example from EOPL chapter 2. We go to the repository and open the examples. So far we have looked at the examples of creating data abstraction by creating an interface of procedures, right? We look at the environment, how it can be the interface can be defined using a data structure abstraction or a procedure abstraction, and then we look at the lambda calculus representation, and then look at the occurs-free procedure that uses that interface to that abstraction. Right? So we can we can construct this kind of data, and then we have a way to take it apart and do useful things with it. So in this video, we're gonna go on to the next section of the chapter and look at this tool, this define data type form we have in this EOPL language that allows us to define this kind of recursive data type more easily, more conveniently, and how we can use this to build a abstract syntax tree, right? Using this data to build a tree that represents the structure of lambda calculus expression, which is this programming language, and then we'll focus on this and see what we can get from this, and why is this useful for building this kind of data structure. So we're going to look at the first one. So a tool. So there's a tool called a define-datatype. This is a form. So what this does is, here's a concrete example. So this allows us to define a data type. I'll give it a name, and then this allows us to define. Okay, so actually I'm going to copy this. I think I have a missing line break there. I'm going to show you this one. Oh no, not this one. Our programming interface. So we're going to I'll add the line break so it's easier to read. Now, okay, so this is called define data type. So this is available in the EOPL. I'm gonna run it. It's available in the EOPL language. Oh, okay, let's see. Yeah, I'm going to define it. So it has a missing definition. So I'm going to define it. So this, we need a procedure. So given x, so we're going to say is it identifier, which is synonymous to whether this is a symbol. Okay, so run. It's imported from this define data type is defined in the EOPL language, so it's given to us. So this allows us to define a data type called this with a name, and then a predicate. Okay, this is for free. Let's give it for us, because we are required to define the variants, right? So the different the possible kind of things this can represent. So the lambda calculus expression can be a variable expression. That's the name of a variant. This is another variant. This is another variant. Okay, each of this this define data type tool will generate those procedures for us. So we're gonna have, for each variant, it's gonna generate this. Oh, actually, wrong. It's gonna generate this thing for us. It's a procedure. It's a constructor, and then also by defining this variant, we provide a list of fields and their predicates. So a validator. So we're saying that var expression, it consists of one field we call it a var, and those names are useful in we'll talk about that in a moment. And then there's a predicate. A predicate basically is whatever procedure we define that can be used to validate the input. Also, whenever we call we use var to construct a variant of this kind, we have to provide a parameter, which is the field, the one and only field, and then this procedure we provide will be used to validate. So if we indeed provide identifier, it's gonna pass, it's gonna succeed. But if we passing something invalid, not the type we expect, it's gonna fail fast. It's gonna give us an error, so it will stop right there. So that's what the defined data type, this contract is, right? We have to provide those predicates, but it's up to us what field we name and the predicate we specify. So now you can see here we're actually using the predicate we're getting for free, right? Since we're enumerating all the variants, so defined data type will be able to generate this procedure that can be used to test whether this field, when it's provided to us, to the constructor, is indeed will indeed pass, cause the predicate to return true, will validate. Okay, so as you can see, this we're following the lambda calculus expression grammar, right? Gonna create a variable, and we represent, the only thing we need to remember is the name of the variable, so it needs to be identifier or a symbol. And then for the body part, for the lambda expression, we need to remember two pieces of information: the bound variable, the parameter, and the body, which is can be any valid lambda calculus expression. So the rater, operator, and operand, and that's that. Okay, so now with this, we'll be able to create lambda calculus expressions. We'll be able to build this kind of abstract, this data structure that represents a lambda calculus expression. And then we'll be able to use this data type, okay, to implement this occur-free procedure again. But this time we're using the new representation we have created using the defined data type. Okay, so let's actually look at this example. I'm gonna copy it and we'll walk through this. So that's so far we have defined this data type. So this will generate the interface procedures for us, so it's a lot easier to use than to come up with the procedures ourselves, right? It's just a productivity tool. It keeps it simple. Now recall that occur-free is this procedure. Given a search variable and a representation of the expression, it's going to tell us whether this variable occurs free in the expression or not, using the set of logic that we have gone through. So this is the same program. It's a program that implements the same function, except that we're using the new defined data type, this interface generated by defined data type. So let's look at this. So so defined data type is often used together in combination with the cases form. So this is a new form. So what this does is it allows us to name a type and then a variable that has this data that reference a type data, a piece of data of this type, and then we can list the variants. So it's like the case form, a switch case statement in many languages. So this allows us to tell this apart. So to decide to distinguish the different variants, and for each variant we get to do different things. Okay, so here is the syntax. We list the type and then the variant, right? And then for each variant in parentheses we can list the fields. So it's by position. So if there's one variable, it's gonna be just that variable, that field name. But if it's more, then it's mapped to this by position. So this will be the first field, this will be the second field, and then we usually name them the same. So now, given this, so if exp is indeed a lambda calc expression and is indeed a var expression, then this allows us to extract var, the field. So now we get to do something with the var. So for recurse free, then the result is really whether the var is the same as the search var. If there's the same, it's occurs free. If it's not, then it's false. Okay. For the lambda expression, we have this logic, but here to get the to take apart the representation and to get what we want is super easy. It's a yeah. So we have the search bar. Let's run it. Oh, get a double. Okay, so delete that. Oh, we have two copies. Okay, so we have var and the search var, and then they are, yeah, so this, okay, so this actually help us. So we don't need to do anything because this syntax already takes a lambda calculus. If it's exp is a lambda expression, it's gonna give us the two fields, so we can use it directly. We don't need to do the current curter, that sort of things, right? So similarly for app expression, we can take it apart this way, and then we can call the methods accordingly. So to demonstrate, I'm going to run some test cases. So here is the first one. So occur free is y. Does y occur free in this variable expression? So we're going to use the interface we have generated by define-datatype to construct a variable expression. Since occur free is defined based on this data type, and the interface we have created using define-datatype, so we can, this is the correct parameter we need to pass in, right? So we construct one, and then the occurs free is going to take that representation of variable expression and then do the right thing. Okay, so note that we don't know what the actual representation is, right? So var express is just a constructor generated by this tool, right? So this is what the representation independent means. So we have an interface, right? From a client perspective, all we need to know is this interface and how to use it. So how to construct and how to take it apart, but how the actual internal representation, internal structure is irrelevant to us, right? So I'm gonna demonstrate one of each. So if the expression, the representation is constructed properly using the constructors we have from define-datatype, this is gonna work, right? Because occurs free is defined in terms of this new data type, this the interface to this data type. And even though we don't know what's inside, what the actual representation is, and we can still use it. In fact, I'm going to show you. Let's try this. So what is that? So it gives us something like a textual representation. So it says struct this and this. So it kind of makes sense. So, but really, what's inside? It looks like a tag list, or it doesn't look like it. So it's it could be anything, but it doesn't matter to us. So similarly, lambda expression. So it does show us that some there it looks like a vector, and then there's an element. There's the the bound variable is captured, the body of the lambda expression is captured, and since the body is just a variable expression, so it's we have x captured somewhere. So this is yeah, so this is introduction to this defined data type form, right? So it's a little bit mysterious and magical to us, but that's really the goal, right? So this, I think the textbook called this a domain-specific language, right? So we have this task of defining this interface, this set of procedures that represent this interface, but this is tedious. We don't want to do it ourselves. It's also error-prone, right? So, but this tool allows us to define it conveniently, and then it does a lot of things for us, generate those procedures, give us the predicate, and then at the end of the day, we accomplish our goal. We have this data type we can use, so we have a way to construct things, and then we have a way to take it apart and make use of it. So that's the overall goal. So in the next video, I'm going to show you the next example, how we can use it for parsing some concrete syntax, and then try to build a data structure that represents this syntax, this program. We call it the abstract syntax tree, and so that we know the structure of the program, and when we interpret the program, we need to identify the different parts and do the right things to them. So I'm gonna stop here, and we'll continue in the next video.